Good morning, all of you. Today we will discuss about the strength of metal. My name is Sabir Khan, and today's topic is deflection and slope introduction. Basic introduction of deflection and slope. Whenever we applied any load on a beam, then the beam will deflect. Like okay, so beam will deflect like this. If this is a beam and this is simply supported beam, then if I applied any external load on that beam, then beam will deflect like this. So that is called as a elastic curve. Okay, so like beam is deflected like this, and if I take a point P and P dash, P is the original point on curve, and P dash is the point after deflection. Okay, so if that is a distance x and y, then P dash is dx and dy, distance apart from P. So that is very small distance, so ds is taken as a linear, and ds square is equals to dx square plus dy square. Now ds is equals to dx square plus dy square. Okay, ds is equals to dx square plus dy square, that is rd alpha, and 1 by r, that is equal to d alpha over dx square plus dy square, where 10 alpha is equals to dy by dx, because that is the um, because that's similar in this triangle, that is dy dx, and this is alpha, so tan alpha become that the dy by dx. Okay, so differentiating tan alpha, so that is sec square alpha d alpha, and dy by dx, that is d square y by dx square into dx. So we put the values of sec square alpha in terms of tan alpha, because we know the values of tan alpha, that is dy by dx. So we put the values of sec square alpha, that is 1 plus tan square alpha d alpha, and that is equal to d square y over dx square into dx. So 1 plus dy by dx, we put the values of tan alpha, that is dy by dx. So 1 plus dy by dx whole square d alpha, that is equal to d square y over dx square dx, and d alpha, that is equal to d square y over dx square, and this quantity will take into the denominator. So dx square plus dy square under root, that is equal to r d alpha, and we put the values of d alpha here, that is that d alpha value we put here, so that become a complex system. And then we put take the dx common, so dx is equals to under root 1 plus dy by dx का whole square, that is equal to r d square y dx square dx 1 plus dy by dx whole square, that is dx here. So 1 by r is equals to d square y over dx square over 1 plus dy by dx whole square, that power 3 by 2. So dy and dx, that is a small quantity, so we can neglect that small quantity square here. So 1 by r is equals to d square y over dx square. And from bending equation, if you remember bending equation, that is okay, m by I, that is equal to E by R, and that is also equal to bending stress madness is stressed by what? So from this equation, m by I is equal to e by r. So I can say that m is equal to ei by r. So m is equal to ei by r, and 1 by r is equal to dv square by over dx square. So m is equal to ei d square by over dx square. So that is our deflection equation. You can find out the deflection as well as slope from this equation. Um, by integrating this equation, we can find out the slope dy by dx, and by double integrating this equation, we can find out the dy by dx. Deflection. That is what. So that is easy for us. Now, sign convention. So if sagging movement is there, then we have to take the positive sign, and if fogging movement is there, so we have to take the negative sign. Okay. So initial beam positive deflection, downward deflection is taken as a positive, and upward deflection is taken as negative. Okay. And slope, if positive x-axis, the up clockwise slope, that is taken as a positive, and x-axis is anti-clockwise slope, we have to take the negative value. Okay. That being shows sign, so we take that positive, fogging that is negative. If we talk about deflection, then upward deflection is negative and downward deflection is positive. Okay. So and when we will integrate that equation, then we will find out, we got this equation eiy, that is equal to minus mx dx plus c1 plus c2, c1x plus c2. Okay. So you have to find out that c1 and c2, these are the constant integration in constant. So to find out the values of c1 and c2, we need some boundary condition. So if I'm talking about the simply supported beam, so we know that the at x is the distance from support A, then x is equal to 0. We have this deflection is equal to 0, because at this support there is no chance of deflection in vertical direction, and in similar way at x equals to L, the deflection is equal to 0. In fixed beam or cantilever beam, I know that x is equal to 0, y is equal to 0, as well as x equals to 0. The slope at the fixed support is 0. Okay. So these are the two boundary condition, because we need to find out the values of C1 and C2. We had two unknowns, so we need two equilibrium equations. So we need two boundary conditions. In similar way, if I'm talking about the overhanging beam, one side overhanging, then x equals to 0, y is equals to 0, x equals to L, y is equals to 0, and two side overhanging, x equals to a, y is equals to 0, x equals to a plus L, y is equals to 0. Okay, so that are the boundary conditions here. So I hope this is clear to all of you. So thank you very much. If you have any doubt, you can contact me.